All right, so definition of an arithmetic sequence. Suppose we have terms of a sequence like this. Such that if you were to take the second term and subtract off the first term, you get the same thing as if you were to take the third term, subtract off the second term, which would be the same thing to say of subtracting the third term off from the fourth term, etc. And if you were to subtract from the nth term in general, the n minus 1th term, if for all of these differences you get a common number, D, we call this common number a common difference. So D is called a common difference. And all arithmetic sequences possess a common difference. So in order to go from any term in this arithmetic sequence to the next term, we would add the common difference. That's what characterizes an arithmetic sequence from other sequences, right? If you have a common difference. All right, now what I'm going to do is I'm going to, with that definition, I'm going to derive a formula called the nth term rule formula for an arithmetic sequence. Here's our first term of our arithmetic sequence. The second term of our arithmetic sequence is found by taking the first term and adding to it the common difference. The third term of our arithmetic sequence is found by taking our second term and adding the common difference. But we have a name for our second term. It's really the first term plus the common difference. So I'm going to substitute in this in for the second term, in which case I'll really have the first term plus the common difference plus another common difference, which gives me my first term plus 2 times our common difference. Our fourth term is found by taking the third term and adding the common difference, but another name for the third term now is the first term plus 2 times the common difference. So that this can be substituted in for the third term, in which case I have this here. So the fourth term is really going to be the first term plus 3 times your common difference. The fifth term is found by taking your fourth term plus your common difference, but the fourth term is the first term plus 3 times your common difference. So the fifth term can be rewritten after substituting this in for your fourth term as the first term plus 3 times your common difference plus your common difference, or your first term plus 4 times your common difference. And hopefully by now we can start to see a pattern emerging. What I want to do now is I want to take a leap of faith, and I want to write my nth term rule for any term of an arithmetic sequence. In order to do that, we need to realize that every term written above has the first term present in it. And it also has a common, we're also adding so many common differences to the first term. To write the nth term rule, we need to realize the relationship that exists between the term index and the number of common differences we're adding to the first term. In other words, the second term has me adding 1 common difference. The third term has me adding 2 common differences. The fourth term has me adding 3 common differences. The fifth term has me adding 4 common differences. Technically, the first term up here has me adding 0 common differences. So can anybody tell me how the number of common differences we add to our first term relates to the term index? How does 0 relate to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5? So what's going on here? Anybody see a pattern? It appears the number of common differences we add to our first term lags 1 behind the term index. So the nth term can be found in by taking your first term and adding to it n minus 1 of your common differences. This is an important formula. This is a formula you want to memorize. It is the nth rule for an arithmetic sequence. This rule will generate any term of an arithmetic sequence. Now, we can also write a recursive definition for an arithmetic sequence. Given the first term, any nth term can be found by taking the previous term, which is the n minus 1th term, plus the common difference. This is a recursive rule or recursive definition for an arithmetic sequence. Normally, we use the nth rule. We don't use the recursive rule, but nonetheless, this would be how the recursive rule would be for an arithmetic sequence. Any questions about that? No. All right.
Can you go back to that for 1 sec so I can write it down? I didn't see it. All right.
Now, this is also shown in section 8.2 of your textbook. All right. All right, now I'm going to show ourselves some sequences, and we're going to ask ourselves whether or not the sequence is arithmetic. So is this infinite sequence an arithmetic sequence? Well, to be an arithmetic sequence, again, it must possess a common difference. Does it? So is 25 minus 35 equal to 15 minus 25 equal to 5 minus 15?
Yes.
Does appear to be. And therefore, our common difference would be negative 10. And so, yes, this would be an arithmetic. This is an arithmetic sequence, all right? All right, this sequence right here. Is it arithmetic? So is 5 minus 1 equal to 10 minus 5 equal to 16 minus 10 equal to 23 minus 16? Well, this gives you 4, and 10 minus 5 gives you 5. So we don't have a common difference here. So this would not be an example of an arithmetic sequence. So any question about how we determine whether a sequence is arithmetic or not? As long as it has a common difference, it's arithmetic, but if it don't, it's not. All right, I want to write the first 5 terms of the arithmetic sequence, where I'm going to give you the first term is negative 4, and I will provide you with the common difference of 4. So how do we write the first 4 terms? Well, first 5 terms rather. We know the first term is negative 5. The second term is going to be the first term plus the common difference, which is negative 5 plus 4, which is negative 1. The third term is going to be the second term plus the common difference, which is to say it's going to be negative 1 plus 4, which is 3. And the fourth term is going to be the third term plus the common difference, which is to say it's going to be 3 plus 4 or 7. And finally, the fifth term is the fourth term plus the common difference, which is to say it's going to be 7 plus 4 or 11. And so therefore, the first 5 terms of this sequence are going to be right here. All right, any questions about how we did that problem? Okay, now I'm going to take this problem further. I'm also going to insist that we find the 100th term of this sequence. Now, the long, laborious way of doing this is to continue adding 4 till we get up to the 100th term, which is going to take forever. You got to be an easier way. The easier way is to use our nth rule we developed on the previous page. So using our nth rule, which is to say it's the first term plus n minus 1 times your common difference, we can easily find the 100th term by letting n be 100 in this rule. So the 100th term is going to be the first term plus 100 minus 1 times your common difference. Your 100th term is going to be your first term, which is -5, plus 99 times your common difference, which is 4. So this is going to be -5 plus 4 times 99. It's 396 plus -5 is 391. And so 391 would be your 100th term for that sequencer. Any questions how we found the 100th term using our nth rule? All right. You ready? All right. Suppose you want to find the 9th term or the arithmetic sequence. Where the first term is -4 and the 22nd term is 164. All right, what we don't know is we don't know the common difference. To find it, we can use our nth rule we developed. For an arithmetic sequence. Now, I know my 22nd term, which is 164. So using my nth rule, I can let n be 22. That's my 22nd term, which is really my first term, plus 22 minus 1 times my common difference. But we know the second term is 164, so we set this equal to 164. This is our 22nd term. And we know our first term is -4. Therefore, we can solve this equation now for a common difference d. So we got -4 plus 21d is equal to 164. Adding 4 to both sides, we get 21d is equal to 168. Divide both sides by 21. And therefore we get our common difference is going to be what, 8. Okay. So now we know our common difference is 8. We still have to answer the question, though. I want to find the 9th term now. Well, now that we know our common difference is 8, we can write our nth term rule for this particular arithmetic sequence. Our nth term is really going to be our first term, which is -4 plus n minus 1 times our common difference of 8. We can simplify this by distributing the 8 inside the parentheses, combining like terms, and therefore we get our nth term rule is going to be this right here. Now we can find the ninth term by letting n be 9. Therefore, our ninth term is really going to be 72 minus 12, which is going to be 60. And that is your ninth term, and we're done with this problem. Any questions about how we did that problem? All right, we'll got that one accounted for. All right. Next one. Find the number of terms for the finite arithmetic sequence. All right, so we have a finite arithmetic sequence here, and we need to know how many terms are in this sequence. In other words, this is my first term, second term, third term, fourth term, but I don't know what term this is. I don't know if this is my 10th term, my 20th term, 50th term, I don't know. This is all we know right now is we can say this is our nth term. We need to find n. That's what we need to do is find n. We got to find out what term this is. All right, to do that, we can use our nth rule, but we're going to need our common difference here first. So my common difference is going to be what? It is an arithmetic sequence. So all you got to do is take any term and subtract off the previous term. So 3 minus 7 is -4. That's your common difference. And your first term is 7. So using our nth rule here we go, using this formula again. It's going to help us out here. So therefore, the nth term, which is -113, is set equal to the first term, which is 7 plus, we don't know n. We know our common difference is -4 though. We have to solve this equation for n, and then we will know what term this is, okay? So solving for n, distributing the -4 inside the parentheses here. This is going to give me, should I distribute here? -4n plus 4. -113 is equal to 11 minus 4n. Solving for n now. -4n, we subtract 11 from both sides. And this is going to give you -124. Divide both sides by -4. And we get n is equal to 31. And there you go. So therefore, this must be the 31st term. So this is your 31st term here. So there are 31 terms in the sequence. So now we know how many terms are in the sequence. And that's what we want to find out is how many terms are in the sequence. There's 31. Any questions? How we found that? 31 terms. Okay. Here's another typical problem. Given the arithmetic sequence where the first term, or excuse me, the 15th term is 49, and the 27th term is 85. We want to find the 500th term. Okay, so to do this problem, we have two problems here, two things missing that we need to know. We got to know the first term of the sequence, and we also have to know the common difference. We don't know those things. So we're going to use, you guessed it, our nth term rule to help us out here. First of all, we're going to look at our 15th term. Our 15th term occurs when n is 15 for this formula. But they tell us our 15th term is 49, so we set this equal to 49. Therefore, we have an equation which says we have our first term plus 14 times our common difference is equal to 49. I'm going to put a box around this equation here. Can you see that there? Now we're going to use our 27th term. Our 27th term has us putting 27 in for n into the nth rule formula, which is really our first term plus 27 minus 1 times our common difference. But our 27th term we know is 85, so we set this equal to 85. Hence, we have another equation. Our first term plus 26 times our common difference is equal to 85. Now, as always, we have a system of two linear equations and two unknowns. We have to solve this system to find the first term and to find the common difference. I'm going to eliminate A1. To do that, I'm going to multiply one of my equations by a -1 and use the elimination method. So I'm going to multiply maybe this first equation here by -1. So I'll multiply this by -1, and I will then get my equivalent equation as being -a sub 1 minus 14d equals -49. Do that, I'm going to add the second equation, which is A1 plus 26d is equal to 85. The a sub 1's drop out, the d's add up to 12. And the right-hand side adds up to what? Is that 36, I believe? Divide by 12, and we get d is equal to 3. So now we know our common difference is 3. Find our first term, we can grab one of these equations. I'm going to go with the first one and substitute 3 in for d and solve for a sub 1. And now I'm going to solve for A1. So I put 3 into here, solving this equation for A1. Subtract 42 from both sides. We discover that our first term is really 7. And now we know our first term of our arithmetic sequence. Now we can write the nth rule. The nth rule is going to be a sub n is equal to our first term, which is 7. Plus n minus 1 times my common difference, which is 3. Cleaning this up or simplifying this, I have my nth rule as being 7 plus distributing to 3, 3n minus 3. My nth rule, therefore, is going to be 4 plus 3n. Now we can answer the question. What's the 500th term of this arithmetic sequence? We let n be 500. So the 500th term of this arithmetic sequence is going to be 1504. And we're done. Okay. So, does that make sense how we answered that question there? We had to solve a system of two linear equations and two unknowns to find out what our two unknowns were, namely the first term and the common difference. But that is the method that is shown in your textbook, so I'm adhering to this method. It's not the only way I've done this problem, but it definitely is it's a nice way of doing the problem though. That's what your author is showing this technique here. All right. So far we've been working with arithmetic sequences. Now we're going to wrap this section up by looking at arithmetic series. And hopefully we remember from last week what a series is in mathematics. A series is nothing more than the sum of terms of a sequence. So when we start adding up terms of a sequence, we generate what's called a series in mathematics. Okay? We're going to start looking at arithmetic series next. Arithmetic series. All right. Suppose that I have this finite arithmetic sequence here. And I'm going to use this finite sequence to illustrate something very important. I'm going to look at what are called partial sums of this sequence. The first partial sum, denoted as S sub 1, is nothing more than just the first term of the sequence. So my first partial sum is going to be 1. My second partial sum, denoted as S sub 2, is the sum of the first 2 terms of this sequence. And that's going to give me 1 plus 4 or 5. The third partial sum of this arithmetic sequence, denoted as S sub 3, is the sum of the first 3 terms of this arithmetic sequence, which is going to be really the second partial sum plus the third term, which is to say 5 plus 7 or 12. The fourth partial sum of this arithmetic sequence, denoted as S sub 4, is going to be the sum of the first 4 terms of this sequence, which you could write more compactly as the third partial sum plus the 4th term, which is to say 12 plus 10 or 22. Finally, the 5th partial sum, denoted as S sub 5, is the sum of the first 5 terms, or all these terms of the sequence, which more compactly is really the 4th partial sum plus the 5th term, which is going to be 22 plus 13, which is really 35. These are called partial sums. Okay. Now, I want to show you something very interesting here. If you take the 5th partial sum, which is really the sum of the first 5 terms of the sequence, which is really the sum of all the terms of the sequence. And below it, we're also going to put the 5th partial sum, but this time we're going to flip this around. We're going to write the partial sum, instead of from left to right, we're going to write it from right to left. We do that there. Still the same partial sums. They both give you 35. Now we're going to add these equations together, and S sub 5 added to S sub 5 is 2 times the 5th partial sum. Now 1 plus 13 gives us 14, plus 4 plus 10 gives us 14, 7 plus 7 gives us 14, 10 plus 4 gives us 14, and 13 plus 1 gives us 14. So something very interesting occurs here. But adding 14 to itself 5 times is more conveniently represented as taking 5 times what? 14. True? And therefore, the 5th partial sum could have been found by taking 5 times 14 and dividing this by 2, which would still give us 35. So it's very interesting to note what just happened there with this finite example. Now, Having seen what happened with this finite example, I'm now going to extrapolate this to an nth partial sum in general for an arithmetic sequence. But, and we'll see that this carries over also to the nth partial sum. Any questions with what happened there? Pretty interesting, pretty neat. All right, now let's take this to the nth level, if you will, the nth partial sum. So here we go. So the nth partial sum of an arithmetic sequence where we add together the first n terms of an arithmetic sequence is going to be the first term added to the second term, added to the third term, plus the fourth term, plus the fifth term, plus dot, 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 all the way up to the n minus 1th term plus the nth term. Correct? Well, let's write it this way now. This is really the first term plus the second term. But what is the second term? The second term is really the first term plus our common difference. Plus the third term. But what's the third term? What's another name for the third term? Another name for the third term is the first term plus 2 times our common difference. Plus the fourth term. But another name for the fourth term is the first term plus 3 times the common difference. Plus the fifth term, but another name for the fifth term is the first term plus 4 times the common difference. Plus dot, 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 plus all the way up to we add the last term, the nth term. Underneath here, I'm going to represent the nth partial sum again, but this time I'm going to flip things around. I'm going to add these terms from right to left instead of left to right. Now, in order to do that, we need to realize that if these are terms of an arithmetic sequence, to go from a term back to the other term, to the previous term, we're going to have to subtract off the common difference. Not add it, but subtract it off, as opposed to going forwards from a term to the next successive term. We add the common difference. To go backwards in an arithmetic sequence, from one term to the next, we subtract off the common difference. So that we need to understand. So I'm going to start with my nth term, and then to go back to the previous term, the term that's previous to the nth term, which is the n minus 1th term, I'm going to have to take my nth term and subtract off my common difference. To go 2 terms back previous to the nth term, I'm going to have to take my nth term and subtract off 2 common differences. 3 terms before my nth term, I will have taken my nth term and subtracted off 3 common differences. 4 terms before my nth term is found by taking my nth term and subtracting off 4 times the common difference. Plus dot, 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 plus till we get all the way down to the first term. Okay. Now, if I add these equations together, partial sum added to a partial sum, nth partial sum added to nth partial sum is 2 times an nth partial sum. First term plus the nth term is the first term plus the nth term. Now, when I add these guys together, what drops out? Notice the D's drop out. The common differences cancel out, leaving me with my first term plus nth term. When I add these terms together, the 2 D's drop out. They add up to 0. They cancel out, leaving you with your first term plus your nth term. In fact, all these are going to cancel out, leaving you each time with your first term plus your nth term. All the way on down the line to the end. Well, we can write this more compactly because how many times did I add the first term and the nth term together? How many times is this? Anybody? I've added this to itself n times. So an easier, more compact way of writing this is to say n times your first term plus your nth term. Now we can solve for our nth partial sum. By dividing both sides of this equation by 2, we get our nth partial sum formula for an arithmetic sequence. So if I add the first n terms of an arithmetic sequence again, I get an nth partial sum, which is to say it's n divided by 2 times the sum of the first and the nth term. This is a very important formula. This formula will give you the sum of the first n terms of an arithmetic sequence. So that's a very important formula. So to know the sum of the first n terms of an arithmetic sequence, we need to know how many terms we're adding together. We need to know the first term and our last term, our nth term. That's a very useful formula. And you see how this was derived above here. By the way, this derivation is also shown in section 8.2 in your textbook. Okay. So let's have a little bit of fun with this formula. Suppose we want to find the sum of the first 100 terms of the sequence 2, 4, 6, 8, 10, 12, etc. So we want to find the sum of the first 100 terms of this sequence, and it does appear to be arithmetic in the sense that it does have a common difference, which would be 2. Common difference is 2. The first term of which is 2. Well, in order to find the sum of the first 100 terms, we use our sum formula we developed above here. It's going to be equal to 100 divided by 2 times your first term plus your 100th term. Now we know our first term, but we don't know our 100th term. We don't know our 100th term in the sequence. So to find it, we're going to use our nth rule. Our 100th term, therefore, is going to be the first term plus 100 minus 1 times your common difference, which means your 100th term is going to be your first term, which is 2 plus 99 times your common difference of 2, which is to say 2 plus 2 times 99 is 198. So 200 is our 100th term. It's our 100th term of this arithmetic sequence. So 200 is our 100th term out here. So now we can find the sum. So the sum of the first 100 terms of this arithmetic sequence is going to be 100 divided by 2 times 2 plus 200, which is to say it's going to be 50 times 202. And what is 50 times 202?
Can you move your paper down a little bit?
It's going to be 10,100. There you go. So that'd be the sum of the first 100 terms of that arithmetic sequence. 10,100. So if you were to add the first 100 terms together here, add all these up all the way up to 200, you get 10,100. So do we see how we use that sum formula to take care of a problem? A very typical problem that you'll run into on Alex. All right, so we added up the first 100 terms. That one right there. And the question is how we did that one there. So yeah, there's just some formulas you want to memorize. The nth rule formula we developed a ways back, and this one right here. That's why I'm boxing these in. They're pretty important. All right, we got this. All right, let's try to evaluate this summation here. All right, so to evaluate this summation, I want to add together the first 200 terms of this sequence. The first 200 terms I want to sum up or add up. So we need to evaluate this series here. This is an arithmetic series. To do so, I'm going to list the first couple of terms of this series so I can see what the terms of the sequence are doing here. I'm going to let I be 1. So we have 3 times 1 plus 5. Plus then I'll let I be 2. So I'll have 3 times 2 plus 5. Plus dot, dot, dot. You could go on forever, but we're not expected to take this all the way up to the 200th term. I don't. That would take way too much time. We want to start making use of our formulas we learned. So the first term here is going to be 8, plus the second term appears is that's going to be what, 11. And I want to add all the way up to my 200th term. Now the common difference here looks like it's going to be 3. 11 minus 8 is 3. First term of which is 8. So the sum of the first 200 terms is going to be equal to 200 divided by 2 times our first term plus our 200th term. We know our first term, but we don't know our 200th term. We have to find our 200th term. To do that, we use our nth term rule. So our 200th term is going to be found by taking our first term plus n, which is 200 minus 1 times our common difference. So our 200th term is going to be our first term, which is 8, plus 200 minus 1 is 199 times our common difference of 3. So our 200th term is going to be 8 plus 199 times 3, which is 597, which is 605. So our 200th term is 605. So plus all the way up to 605. We want to add all these up. Well, the way to do it is to use your sum formula. So therefore, the sum of the first 200 terms is going to be equal to 200 divided by 2, which is 100, times your first term, which is 8, plus your 200th term, which is 605. And this will give it to us. So we got 100 times 605 plus 8. And I get 61,300 for the sum of the first 200 terms of the sequence. Or so 61,300 would be the evaluation of this arithmetic series. And that's your answer. Any questions on how we did that problem here? All right. Okay, well, that there. Let's see here. We have time for classwork. See if I can find it. All right, we can call this maybe classwork number 1. Evaluate this sum here. K goes from 1 to 1,000. So I want you to evaluate this summation here, or this arithmetic series, which means we're going to have to add the first 1,000 terms of the associated sequence defined by this nth term rule. So go ahead and see if you can evaluate this. I'll give you a couple minutes to work on this. It's done essentially the same way as the one above here was done. All right, now I want you to add together the first 1,000 terms. All right, go ahead and do that. Please try not to do this problem the long way. We won't have enough time, so please try to use your formulas as much as possible.
Can you move your paper down?
All right, I'm just working this out here. Did anybody get the answer? It's a big number. Okay, so the sum of the first 1,000 terms of that arithmetic sequence is like 2,005,000. Anybody get that?
Yeah.
Yeah.
2,005,000. That's the sum of the first 1,000 terms. So you got to find your 1,000th term. And notice I use my formulas here. I use my nth rule formula and also my sum formula to take care of this problem. Because to do it the wrong way, well, it will be a long time to get that result. So try to make use of your formulas. So I don't take the sting out of these things here. All right, we're done with that section. Now we're going to get into geometric sequences and series, right? So what characterizes a sequence as being arithmetic? Well, the sequence must possess a common difference. Okay, so what characterizes a sequence as being a geometric sequence? Well, in order to be a geometric sequence, the sequence must possess not a common difference, but it must possess what is called a common ratio. Are we done with this here? So section 8.3 is the last section today. It's entitled Geometric Sequences and Series. So what makes this sequence a geometric sequence? Well, it must possess what is called a common ratio. And the common ratio R is going to be equal to any term divided by the previous term. So when you take a term of a sequence and divide it by the previous term, if you keep cranking out the same number called the common ratio, then the sequence is a geometric sequence. So to move from any term to the next term, we multiply by the common ratio. Okay, that's how you progress from one term to the next term in a geometric sequence. All right, I'm going to develop an nth term rule for a geometric sequence. They was in the same way, in a similar way rather, that I developed a rule for an arithmetic sequence. First term of a geometric sequence is a sub 1. The second term, denoted as a sub 2, is really made possible by taking your first term and multiplying it by the common ratio. The third term of a geometric sequence is found by taking the second term and multiplying it by the common ratio. But we have a name for the second term. The second term is the common ratio times the first term. So we substitute this in for the second term. And therefore, the third term is really the common ratio times the common ratio times the first term, or the common ratio squared times the first term. The fourth term is found by taking the common ratio times the third term. But substituting in for the third term, r squared times a1, the fourth term is really the common ratio times r squared times a1, which is really the common ratio cubed times the first term. The fifth term is found by taking the fourth term and multiplying it by the common ratio, but that's equivalent to saying the common ratio r times r cubed times the first term, or r to the fourth power times the first term. Now we are able, hopefully, to see a pattern in which we can now develop an nth term rule for a geometric sequence. To do that, we need to realize that every term listed above has the first term present as a factor, and it also has so many powers of the common ratio. Technically, the first term up here does have the common ratio as a power. It's just that it's r to the 0th power times the first term. R to the 0th power being 1. So how does the power on r relate to the index of the term? How does 0 relate to 1, 1 relate to 2, 2 relate to 3, 3 relate to 4, 4 relate to 5? You can see that the power on r lags 1 behind the term index. So the nth term of a geometric sequence is going to be the first term times the common ratio raised to the n-1 power. This is a very important formula. This is called the nth rule of a geometric. I'm sorry, somebody have a question? This is the nth rule of a geometric sequence. This rule will enable you to generate any term of a geometric sequence, provided you know the first term and also the common ratio. A recursive definition in passing would be this: knowing the first term of a geometric sequence. To find the nth term, we would take the previous term and multiply it by the common ratio. So this would be a recursive definition that shows you how to move from one term to the next term of a geometric sequence. Recursive rule. Now, we don't really use recursive rules really too much for arithmetic or geometric sequences in this course, but it's wise to at least see this, especially if any of you eventually maybe get into some computer programming. In computer science, recursion does have its place, all right, and is used, not a lot, but is used once in a while in writing code for a computer, all right. All right. So we now have an nth term rule for a geometric sequence. Any questions about anything on this page here? All right. Is the sequence geometric? So given a sequence, we should be able to test it to see if it is a geometric sequence. So is this sequence a geometric sequence? Does it have a common ratio? Is 6 divided by 18 equal to 2 divided by 6? And is that equal to 2/3 divided by 2? Is that the case? 6 divided by 18 appears to be reduced down to 1/3. 2 divided by 6 also reduces down to 1/3. Looks like we got something going on here. But what's 2/3 divided by 2? Is it also 1/3? Well, 2/3 divided by 2/1 is really 2/3 times 1/2, which is really 1/3. So yes, we do have a geometric sequence where the common ratio is 1/3. In other words, you'd have to multiply 18 by 1/3 to get 6, multiply 6 by 1/3 to get 2, multiply 2 by 1/3 to get 2/3, et cetera, et cetera, et cetera. So this is a geometric sequence. How about this next sequence, 3, 12, 48, 240? Is this a geometric sequence? Well, if it is, then 12 divided by 3 has got to be equal to 48 divided by 12, which has got to be equal to 240 divided by 48. Is that the case? Well, 12 divided by 3 is 4, and 48 divided by 12 is 4. Looks pretty good so far. What's 240 divided by 48? Well, that gives you 5. So we do not have a common ratio. So this is not a geometric sequence. Any questions how to test whether a sequence is geometric or not? Must have a common ratio. All right, we want to write the first 4 terms of the geometric sequence where the first term is provided for us as being 5, the common ratio is -2. Well, it should be pretty easy. The first term is 5. To go to the second term, we just multiply this by what? By -2. And we get -10. To get the next term, we multiply this by -2 and we get +20. To get the fourth term, we multiply this by a -2 and we generate -40. There you go. We listed the first four terms of this geometric sequence here. This is your first term, second term, third term, and your fourth term. And since the sign of each term switches from positive to negative, we call this an alternating geometric sequence. An alternating geometric sequence. Because those terms alternate sign. All right. Makes sense how we wrote the first four terms. So I'm going to try to write the nth rule for the following geometric sequence. 2, 3, 9 halves, 27 fourths. To write the nth rule, of course, we need to know the nth rule formula, which is this right here we developed earlier. So we're shooting for that formula. Right? We need to know the first term and we need to know the common ratio. Well, the first term is 2. Now, what's the common ratio? Common ratio is going to be 3 divided by 2, or it'll be 9 halves divided by 3, or it'll be 27 fourths divided by 9 halves. In each case, you do get 3 halves. So that's your common ratio, 3 halves. So to write the nth rule is pretty simple. Your nth term, any nth term of this geometric sequence is found by taking your first term, which is 2, times the common ratio, which is 3 halves, raised to the n-1 power. You got your answer. That's your nth rule of that geometric sequence. So this rule could be used to find any term of that geometric sequence. I mean, you could even find, the 100th term. Suppose that we wanted to find the 100th term for this geometric sequence, which is way out here. Well, we could use our nth rule here. So the 100th term would be equal to 2 times 3 halves raised to the 100 minus 1 power, which is 2 times 3 halves raised to the 99th power. Now you get on your calculator and see if we can dial this up. I would like my final answer to be as a fraction, so I may have to hit my math button and select the frac function. So I'm going to take 2 times inside parentheses 3 divided by 2 raised to the 99th power. And I do get a messy decimal, but if I hit here, I'll show you what I got here. I got a messy decimal after doing that, but now I would like to turn this into a fraction. So if I hit my math button and select frac, hopefully this takes care of business, and it doesn't. So I guess we're gonna have to just go with this though. All right, so you can see it's a very big number. It's order of magnitude of 10 to the 17th power. All right, so that's a very big number, but that would be the 100th term of this geometric sequence, which is a humongous number. Everybody understand that there? What happened? Okay, let's put that away. Okay. Now let's see here. All right. That's a typical problem there. Here's a typical problem. Find the fifth term of the geometric sequence where the first term is 15 and the second term is -9. Now, the good news is we do have our first term. The bad news is we don't have our common ratio. So how are we going to negotiate this problem here? You know, well, we're going to use our nth rule. So we're going to use our nth rule for a geometric sequence right there. Now, wait a minute here. Something's wrong here. Oh, okay, no. We can find our common ratio. What am I thinking here? Common ratio is just going to be your second term divided by your first term. So it's going to be -9 divided by 15, which reduces down to -3/5. So -3/5 is your common ratio. So this really isn't that bad of a problem because now we can write our nth term rule. It would be our first term, which is 15, times our common ratio, which is -3/5, raised to the n-1 power. Everybody see that there? That's your nth rule here. First term is 15. And the common ratio is found to be -3/5. We can now use this to find our fifth term. To find our fifth term, denoted as a sub 5, we let n be 5 in this formula. So we got 15 times -3/5 raised to the 5-1 power, which is 15 times -3/5 raised to the 4th power. And it's going to be 15 times, now -3 to the 4th power is going to be -3 times itself 4 times, which is going to be 81. 5 to the 4th power is 5 times itself 4 times, which is 625. And what's 15 times 81? Gives you 1215. So 1215 over 625. And we can just leave it like that. So that'd be your fifth term of that geometric sequence. Everybody see that typical problem there? Okay. Suppose that we're given the second term of a geometric sequence is 80. And the fifth term is 40.96. Suppose I want to find R a sub 1, and I want to find an nth term rule. Okay, so how do we do that here? Well, we don't know our common ratio. We don't know our first term, but we know our nth rule in general. Our nth rule for a geometric sequence is this guy right here. We could use this now. So using the fact that our second term is 80, I'm going to use this rule and let n be 2. So my second term, denoted as a sub 2, is going to be my first term times my unknown common ratio raised to the 2 minus 1 power. But we know our second term is equal to 80, so we set this equal to 80. Therefore, we arrive at an equation that says we have our first term times r to the first power equals 80. I'll put a box around that equation. You see that there? Using my nth rule and the fact that my fifth term is known, I'll let n and my nth rule become 5 to denote my fifth term, which is really my first term times my common ratio raised to the 5 minus 1 power. But our fifth term is known to be 40.96. So we set this equal to 40.96. Therefore, I really have another equation that says A1 times r to the fourth power is equal to 40.96. We have another equation. So we have a system of two equations and two unknowns. A sub 1 and r are known. And since this equation is a nonlinear equation, and this is a nonlinear equation, we have a nonlinear system we have to solve. So to solve this nonlinear system of equations for its two unknowns, I'm going to solve this first equation for a sub 1 in terms of r. So I'm going to solve a sub 1 r equals 80 for a sub 1. To do that, I divide both sides by r. So another name for a sub 1 is 80 over r. I'm now going to substitute this in to the second equation in for a sub 1. So I'm solving the system by substitution. So in for a sub 1, I put 80 over r. So I'll have 80 over r times r to the fourth power is equal to 40.96. Now we can solve this equation for r. Now this is going to be really 80 r to the fourth divided by r is equal to 40.96. But this is really 80 times r cubed is equal to 40.96. To solve for r, I'm going to divide both sides of my equation by 80. And then I get r cubed is equal to, and I'm going to actually do the division here, 40.96 divided by 80 gives me 0.512. Now I'm going to take the cubed root of both sides of this equation to solve for r. So I take the cubed root of the left and the cubed root of the right. Now, on your TI-84 calculator in the math number menu, you do have a cubed root at your disposal. And so the cubed root of 512 thousandths is going to give me 0.8 or 8 tenths. So now we know our common ratio is 8 tenths. So we found r to be 0.8. Find our first term, I'm going to use this equation here because now I know r is 0.8. So to find my first term, I merely take 80 and divide it by 8 tenths, in which case I get 100. So my first term is 100 then. Now we can also find an nth term rule. The nth rule would be the first term times r to the n minus 1 power. So my nth term is my first term, which is 100, times my common ratio, which is 0.8, raised to the n minus 1 power. And that's your nth term rule for this geometric sequence here. And we're done. We've answered all the questions here. We found everything we wanted to find. All right. Any questions with what I'm doing here? You know, it's also wise to be looking over your textbook. The sections that I do cover to go through the examples, I think is very therapeutic and helps to further solidify what's going on here with this material. So please do take time to look through the examples in your textbook. for each section that I go over. That's a wise thing to do. To complement what it is I am trying to convey during these sessions here. Okay, see where we are with the clock here. 1:48. Yeah, it's about right. All right. So up to now, in this section 8.3, we've been working with geometric sequences. We've shown ourselves how to find the nth term rule for a geometric sequence and how to use that rule to answer various questions. Now, to wrap up the rest of this section, we are going to turn over the coin and look at the other side, which is looking at geometric series. Of course, a geometric series is the sum of terms of a geometric sequence. Now, we're going to develop a formula that will give us the sum of the first n terms of a geometric sequence, of a finite geometric sequence, that is. And so therefore it's called a finite sum formula. Some geometric sequences that converge some infinite geometric sequences that converge enable us to find an infinite sum of adding up an infinite number of terms of such a sequence. And I don't know if I'm going to have enough time to develop that formula, as I did not have enough time with my face-to-face section this morning. If I don't have enough time to develop that formula, I will try to make maybe a little supplemental video that goes over developing that infinite sum formula. And I think I may have already made that video in a previous semester. I have to look at it and see if I can find it. But at least developed a finite sum formula for adding up a finite number of terms of a finite geometric sequence. So, all right, so here we go. Finite geometric series. This is the nth partial sum of adding up n terms of a finite geometric sequence. It's the first term plus the second term plus the third term plus the fourth term plus ... all the way up to the nth term. Well, this can be refined though, this nth partial sum formula, because we know the second term of a geometric sequence is really the first term multiplied by the common ratio. The third term of a geometric sequence is nothing more than really the first term multiplied by the common ratio squared. The fourth term is the first term times the common ratio cubed, plus ... all the way up to the nth term, but the nth term is really the first term times the common ratio to the n-1 power. Do we understand that nth partial sum of adding up the first n terms of this finite geometric sequence? I'm going to take this last equation and multiply both sides by the common ratio. When I multiply this term by r, I get a sub 1 r. When I multiply this term by r, I get a sub 1, and r times r is r squared. When I multiply this term by r, I get a sub 1 r cubed. When I multiply this term by r, I get a sub 1 r to the fourth power, plus ... plus. When I multiply this last term by r, what do I get? What's r to the first power times r to the n-1 power? When we multiply like bases, we keep the base the same and add the exponents. So it's going to be r to the 1 plus n minus 1. The ones drop out, leaves me with r to the nth power. So when I multiply this last term by r, I get a sub 1 times r to the nth power. Do we understand what I've done here? I multiplied both sides of this equation by r and generated this here. All right, now I'm going to subtract off the second equation from the one above. So I'm going to have s sub n minus r times s sub n. And I'm going to have this minus this. And then I'll have this minus this term. And I'll have this minus this. And I'll have this minus this. Plus dot, 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 all the way on down the line. We continue to do this until we get to the end here. In which case I will have my last term here is going to be a sub 1 r to the n minus 1 power minus a sub 1 r to the nth power. This is a sub 1 times r to the nth power at the very end here. Okay. Now, an interesting thing occurs here, ladies and gentlemen. When I shift my parentheses, and I will try to illustrate this maybe with a different color, if I can find a different color here. All right. Red, okay? Watch what happens when I shift my parentheses. If I shift the parentheses to include these terms, and I shift my parentheses to include these terms, and I shift my parentheses to include these terms right here. So notice what happens when I shift my parentheses, this cancels out. This drops out with this. This drops out with this. This drops out with this, et cetera, all the way on down the line. These drop out with each other. So what I'm left with then is I'm left with my first lonely term here. This is gone with this. These are opposites. These drop out. These drop out. This would drop out the next one. It's not shown here, but this would be gone. And this would drop out, ladies and gentlemen, with the previous term that's not shown. This will drop out. And at the end, what we're left with is minus a sub 1 r to the nth. So look what happens after all the cancellation up here. We're left with this. Now I can factor out the nth partial sum out of both these terms here. I can now divide both sides by 1 minus r, and I develop a very interesting formula here. The sum of the first n terms of a finite geometric sequence is going to be equal to this right here. By the way, I could also factor out a sub 1 out of both these terms here, leaving behind 1 minus r to the nth power divided by 1 minus r. This is a nice formula to know or to have handy. This will basically give you the sum of the first n terms of a geometric sequence. Sum of the first n terms of a geometric sequence. That's what this formula gives you. Of course, in order to do that, you have to know how many terms you're adding together. You have to know what n is. You have to know your first term, and you have to know your common ratio. Okay, so let's see if we can put that to use here to help us out. Alrighty. And this derivation is also shown in your textbook also. I tried to lay it out as best as possible. But they also show this in section 8.3. Well, let's see if we can use this formula. Okay, so we want to try to evaluate this sum here. And which means we're adding up the first 6 terms of this geometric sequence here. I'm going to list the first couple of terms here. I let I be 1, and I'll have 4 times 1/2 raised to the 1 minus 1 or the 0th power. Then I becomes 2, in which case I'll have 4 times 1/2 raised to the 2 minus 1 power or first power. On and on this goes. The first term, 4 times 1/2 to the 0th power is 4 times 1, which is 4. 4 times 1/2 is 2, and on this goes. You know, the common ratio is actually staring at us in the summation notation. It happens to be 1/2. So R is really 1/2 here. 4 is our first term. This is really the nth term rule for this geometric sequence here. The rule is a sub n is equal to 4 times 1/2 to the n minus 1 power. You see it? This is the nth term rule for cranking out terms of our geometric sequence. So our common ratio is 1/2. First term is 4. So to find the sum of the first 6 terms, we could use our formula we just developed back right here. So we need our first term times 1 minus r to the 6th power divided by 1 minus r. So this is going to be equal to our first term times 1 minus r to the 6th power all over 1 minus r. Which is to say our first term is 4 times 1 minus our common ratio is 1/2 to the 6th power divided by 1 minus 1/2. Now 1/2 to the 6th power, 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 is going to be 1 over 64. 1 minus 1/2 is negative 1/2 down here. All right, so I would like you to get on your calculator, ladies and gentlemen, and see if you can dial this up. In fact, you might want to actually go way back over here and make sure you can do this. Just make sure that you put your denominator inside parentheses. Things should work out okay. But see if you can do this on your calculator, either here or here. Crank this in or put this in, either one. And let's see what we get for a sum of the first 6 terms of this geometric sequence here. So let's see if anybody can do that on your calculator and tell me what we get for our sum. Let me know when you got it, anybody.
What's that number over 64 in the fraction?
Over what?
64 in the fraction. What's on top the numerator?
This is 1 minus 1/64.
Okay.
1/2 to the 6th power is 1 over 64.
Okay.
All right, so see if you can dial it up. Tell me what we get the sum for the first 6 terms of this geometric sequence here.
I got 63/8.
63/8. All right, 63/8. Anybody else get 63/8?
Yeah.
63/8 for the sum. Okay, so 63/8, which you could also represent as a mixed number, as 7 and 7 what, 8s, I believe, correct? You could do that. You could also represent this as a decimal if you want. 7/8 is going to be 875,000. So this would be 7 and 875,000. So I would take the answer anyway here. So anyways.
Would it be a negative because it's divided by the -1/2?
Yeah, well, I think it's a negative over a negative. I think this turns out to be what, let's see.
Oh, that would just be if you're doing like, I meant like the -63/8.
Let's see. Well, these terms are getting what, smaller, aren't they? 4, 2. So did we mess the sign up here? Let's see here. So what is 1 minus 1/64? That would be 64/64 minus 1/64, which is 63/64. And yeah, it looks like it would not be positive, does it? Doesn't look like it. So you got to be careful with your signs here. 64. And then we're dividing by -0.5. So yeah, this looks like it's going to be -7 7/8 or -63/8. Should be -63/8. Now you're probably wondering, where's
The bottom would be positive, wouldn't it be?
what's
'Cause
that?
it's minus a half. Wouldn't that be positive 0.5 though?
Wait a minute. Let me see my denominator. Did I mess my denominator up here? Yeah, that would be 1 minus what? 1/2, right? That would be positive 1/2. No, we don't have it correct there. All right, no, this is still positive. So it is positive 7.875 or 7 7/8 or 63/8. Yeah. Yeah, 1 minus a half is a positive 1/2. Whereas
Okay, that was what screwed me up. I was looking at the second one.
all right. So it should be a positive sum. All right. All right.
Will Alex take any of those answers, or does it have to be the decimal?
Well, you could probably, I would probably leave it as, I'm not 100% sure on that. You will discover that on your homework though, okay?
Okay.
And you get an unlimited number of attempts on homework. I would probably leave this just as a fraction, as at 63/8. That would be me.
Okay, thank you.
That's how I would leave it. So yeah, I would probably just go with that. Okay. So we've seen how we were able to use our sum formula here, our finite sum formula, for adding together the first n terms of a geometric sequence. All right, let's see. Find 5 plus 10 plus 20 plus ... plus 5,120. Wow. Now they want us to evaluate the sum here, and it is a finite sum because we're only adding up a finite number of numbers. But what is the major hangup with this problem here? Anybody know what we're going to need to find out? I want to evaluate this sum. I'm gonna add all these numbers up, 5 to 5,120. But what are we gonna need to know to do this?
The common ratio?
Yeah, we're gonna need to know the common ratio. What do you think it might be?
2.
Kind of looks like 2. All right, we know the common ratio. We know the first term is 5. But there's something else that's that we're gonna need to know. What is it? Something else we got to know.
How many terms there are?
That's right. We don't even know how many terms are adding up here. I mean, I see plus dot, dot, dot there. I don't know how many terms are in between the pluses and the dots, correct? I don't know what term that 5,120 is. I don't know, what is it, the 10th term, the 20th term, the 50th term? I don't know. We got to find that out. All right, because remember, if we're going to use our sum formula here, we got to know how many terms we're adding together here. We got to know what n is. And if we don't know that, there's no way we're going to be able to find it. So why don't we just, at this point in time, just call this our nth term? And you are correct, though. We got to find n. So we have to find what term this is out here. To do that, we could use our nth rule for a geometric sequence, which we developed, which is right here. Bless you. This is our nth rule. Now, we know our nth term is 5,120. So I can let my nth term be 5,120. And that's going to be my first term, which is 5 times my common ratio. You are correct. The common ratio is going to be 10 divided by 5 or 20 divided by 10, which is going to be 2. So our common ratio is 2. But we have to solve this equation for n. Everybody see that there? We got to solve that for n. You know what kind of an equation this is? This is called an exponential equation because n is part of an exponent. Now, ladies and gentlemen, if you came through the ranks of intermediate algebra here at Montgomery College, you should have been exposed to solving exponential equations. That is one of the chapters that is covered in intermediate algebra, along with logarithms. So how would we solve for n here? Well, first I'm going to isolate this base 2 raised to this power by dividing both sides of this equation by 5. How many times does 5 go into 5,120? I think it's, is that 1024? So we got to solve this base 2 exponential equation for n. Now, one way you could do that is you could take the logarithm of both sides of this equation and solve for the exponent n, but you don't have to. This 1,024 can be reduced down to base 2 raised to some power. So if I can reduce both sides of this equation down to the common base of 2, I can then solve for n. So get on your calculator, and I want you to find for me what power you have to raise n to. Excuse me, what power you have to raise 2 to give you 1,024. So what power do you have to raise 2 to give you 1024? Go ahead and find out on your calculator right now. So just start raising 2 to powers, keep climbing the ladder. Eventually you'll hit the power on 2 that will give you the 1,024.
I got 10.
Yeah, it would be 2 to the 10th power. Okay, 2 to the 10th power is 1024. So the left side of this exponential equation could be rewritten as 2 to the 10th power. There is a theorem, ladies and gentlemen, that we can now use. The theorem is very intuitive. It says this: if a to the mth power is equal to a to the nth power, then what must be true about the exponents? if you have equivalence between like bases, then the exponents have to be what to each other? They have to be equal to each other. So therefore, we set 10 equal to n minus 1, and now we just solve for n. Add 1 to both sides, we get n is equal to 11. So you know what we've discovered? What term is this out here? It's our 11th term. Everybody see that there? It's our 11th term. It's our 11th term. So we're really adding together the first 11 terms of this geometric series here. So the sum of the first 11 terms is going to be equal to our first term, which is 5 times 1 minus our common ratio, which is 2 raised to the nth power. My n is really 11 here. And that all sits over 1 minus common ratio of 2. All right, get on your calculator and tell me what this sum is. What is going to be the sum of the first 11 terms of this geometric sequence? Go ahead. And tell me what that 11th partial sum would be. So make sure you're able to do this calculation on your calculator. Dial it in and tell me what we get. Now, in order to stay off a logical error, you probably have to include your denominator side parentheses to force your calculator to subtract 2 from 1 first before doing the division. Because your calculator is going to obey the order of operations. So parentheses are necessary here to force the machine to give us what we want. Let me know if anybody gets the sum of those first 11 terms there.
I got 10,235.
All right, 10,235. Anybody else get that? Anybody else confirm that?
Yeah, I did.
10,235. Okay, you got that too. All right, so, all right, well, that's looking like that would be the result of adding those 11 terms, those first 11 terms together of the geometric sequence, 10,235. And that would be that there. All right. Okay, now. What if I wanted to add together an infinite number of these terms here? Not a finite number, but an infinite number. First of all, would the sum even exist? Would there even be a sum for adding up an infinite number of these terms? Infinite. Well, ladies and gentlemen, the answer is yes, the sum would exist. Because this sequence, this geometric sequence, this infinite geometric sequence happens to be what is called a convergent geometric sequence. You know, this is an example of a convergent geometric sequence. What does it mean to be convergent? Well, it means that these terms are getting smaller and smaller and smaller, and so they're actually converging to an actual value of 0. Isn't that true? These fractions are getting smaller and smaller and smaller as the denominator keeps getting doubled, but the numerator is fixed at 1. So these individual terms of the sequence are approaching 0 or converging, we say, to 0. Because of that, this infinite sum would exist. And I'm gonna develop a infinite sum formula, although I can't do it now because I'm all out of time. And so I may have to make either a supplemental video developing the infinite sum formula for adding infinite terms of a convergent geometric sequence together, or I may have to finish this next time. But I will decide as to what I'm going to do with that. I'll let you know via email, okay? But that's all the time I have for today. We covered a lot of ground. We looked at arithmetic sequences and series, developing two very important formulas, namely the nth term rule and also the sum of the first n terms of an arithmetic sequence. We then turned our attention in 8.3 to geometric sequences and series, developing an nth term rule for a geometric sequence and also a finite sum formula for adding together the first n terms of a geometric sequence. And in 8.3, I will wrap it up by showing ourselves how to add together an infinite number of terms of a convergent geometric sequence. I will show you how to develop that formula either through video or next session. All right, so that is it. I will stay on the line if you have any questions. And I will open up, of course, their sections that pertain to the new stuff that we've just seen today. All right, so it's never too early to get started on Alex to avoid possibly getting behind. Okay. All right, so have a good day, and hopefully I'll see you in a couple of days. I'll be on the line for any remaining lingering questions on anything.
Hello.
Oh, hey, how you